Right, so this is the second half of lecture 5.b. It's going to be pretty short. We've already talked about the first four, actually the first, all five rules, and we just looked at this example where we learned about stitching two pieces together in order to make a longer area. The work for part A, which we just worked out, looked like this. And the idea was if I want to know the area under this curve for all the way from -3 to 6, I can add together the areas from -3 to 0 and the piece from 0 to 6, and altogether I'll get that entire area. Your job right now is to work out B, C, and D, and then I'll show you the answers. And the answer for B is almost identical to the work for A, except that this time we're choosing a different second piece to stitch together. The piece from -3 to 0, and then from 0 to 3 gives you the total value from -3 to 3. Go ahead and try C. So C is a great test of your critical thinking abilities. We're trying to find the area under this same function from 3 to 6. And we know the area from -3 to 0, we know the area from 0 to 6, and we know the area from 0 to 3. But we can't just add any of these pieces together to get the area from 3 to 6, because we would need a piece that starts at 3 and ends somewhere in between, and we don't have anything that starts at 3. So the closest thing we've got to start with is the area from 0 to 6. Obviously, this is a larger region or interval than the one we actually want. What would we have to do to cut that down, to take out the part we don't want? What would we change that by? Yeah, we would actually want to take away part of this area. And the part we'd want to take away is the part from 0 to 3. Now, if you're not really convinced by this, or if you were maybe tempted to write the part from 3 to 0, think about it this way. The additivity property of integrals tells us that the integral from 0 to 3 plus the integral from 3 to 6 is going to equal the integral from 0 to 6, all of the same function. So if I really want to find the integral from 3 to 6, all I need to do is subtract the integral from 0 to 3 on both sides. And when you subtract this over, we get exactly the equation that I have written right here. Convinced? So from there, we just subtract the area under the larger region minus the area under the first section, and we should end up with the area from 3 to 6. All right. D is the last one. Put all of these tricks together. D required two different properties. First, you should have split the integral using the sum and difference rule, which I've missed the addition here. And then after that, you would have wanted to evaluate the second integral by splitting the terms of integration into two intervals. The first one, of course, is one of your given numbers. Adding all the numbers up, you get 25.67, just like that. Okay, so you now know all of the properties, and I want to go over one final example because we haven't really dealt with trig very much, and there's a known trig limit. So this is the sine function, and it turns out that the area under one section of the sine or cosine function, as in you can see what's represented right here, this area turns out to be 2 units squared. That's extremely non-obvious. We have no good way of calculating this, so for now you're just going to have to trust me on that one. But if you take this fact, you can actually then use this fact to calculate a whole bunch of other integrals, also using the fact that both sine and cosine are symmetric. Sine, of course, is symmetric around the origin, cosine around the y-axis, but in general, this shape is symmetrical. So take this fact and see if you can use this fact, the fact that the integral from 0 to pi under the sine curve is 2. See if you can now evaluate these 8 integrals. The answer is, of course, yes, you can, but the question is, can you see how? And my hint is just to think about the areas involved. Go ahead and try A and B, and then I'll discuss how to solve those, and we'll move on from there. So the key to all of these is really going to be the sketch that you draw. You should start by sketching the sine function, and I'm just going to use Desmos to do that. This is what sine looks like, and you should shade on this graph the region that we know. So we know that this area in blue equals 2 units squared. Now, we're wondering about a different area. We're wondering about the area between pi and 2 pi. So we want to mark that as well, which I've now done in green. The answer to the first integral is the area of this green region. Obviously, or it should be obvious, that the area is actually the exact same as the blue area. Now, don't be trapped, and maybe you were when you answered this on Edpuzzle, because actually it's not exactly the same. The difference is that the green area, even though it has the same size as the blue area, the green area is below the x-axis, which means that the green area is considered to be a negative area. Again, that's just a convention. It was discussed in an earlier video. There isn't a good reason for this except that it helps us use integral properties properly. So the answer to the first integral is that we have the same area except it's negative, which means the answer to the integral is -2. In B, the integral that we're interested in is the integral that goes all the way from 0 to 2 pi, which means the area of the blue and the green together. But we just established we know that the blue area is +2 and the green area is -2, so if we add those together to get the entire region, the total area is actually going to be considered 0. And again, that's because the positive area ends up canceling out the negative area. Okay, use this sketch or your own and evaluate C and D. Again, in order to understand C, we start with knowing that this area is 2, and then we try and visualize what area we're actually looking for, which I've done by shading it in purple. And when you look at the picture, it seems pretty clear that the purple is half of what the blue was, which means the answer to this integral should be 1. Now, I don't want you to get too bored with this, so I've added a couple other interesting ones in here. D, we actually end up changing the function. So instead of this normal sine curve, the same shape is shifted up by 2 units. Now, this little circular region is still 2, but the region that we're actually interested in is the region from 0 to pi underneath the entire curve. In other words, it's that curved piece at the top plus the area of this rectangle. Well, rectangles are really easy to calculate. It's just base times height. The base length here is pi, the height is 2, so that's 2 pi plus 2. Now that you've seen a number of these, I'm going to let you go ahead and try the remaining ones on your own. You will see whether your answer is right or wrong in Edpuzzle, but I'll let you be a little curious about this. If you're confused about any of them, please do bring them back to me and we can talk about them when you get to class. Otherwise, that'll be it for this lecture. You should, by the end of this lecture, and certainly in time for the quiz after break, you should understand the 5 properties of integrals and how you use them to evaluate integrals. You should also have memorized the value of the trig integral that we presented at the end. Happy studying!